Good morning, everyone. My name is Xianping Qu. I'm very happy to be here at the SREcon. And my topic today is smart monitoring system for automatic anomaly detection and problem diagnosis. Before we proceed to the topic, I would like to introduce myself a little bit. I'm an engineer of Baidu SRE team. When I joined Baidu 6 years ago, there is no SRE team. And SRE engineers belong to every production team. And now, our team has over 400 of engineers. And we support over 300 of products, and which are developed by about 20,000 of engineers. And my focus areas are system monitoring and data analysis. Here is my email, and please feel free to contact me if you have any questions on my topic. My company, the name Baidu, is a quote from the last line of a poem written more than 800 years ago. During the Song Dynasty, Baidu is the largest Chinese search engine. We have web page search, image search, music search, and video search. Besides search engine, we have many other products such as wiki, forum, news, web directory, maps, and personal cloud storage. So we are all around the internet company. Here is our agenda. First, I will introduce the background, why we developed this smart monitoring system. And second, I will describe our smart monitoring system in detail. The core components of our system include anomaly detection, alarm filter, and problem diagnosis. Last, I will give a brief summary. Chinese internet market had been growing very fast in the recent years. Therefore, Baidu has also grown its service capability extensively. Today, we have hundreds of thousands of servers, which is 20 times more than the number 5 years ago. And our data volume also had an explosive growth. Our current data volume had exceeded 1.5 EB. The number of web pages has exceeded 300 of billions, with a daily increase over 1 billion. The data generated by the monitoring system is over 20 PB, with a daily increase over 40 TB. Such fast growth brings a great challenge to the Baidu SRE team. We need to maintain a lot of complex service and modules. Most of our working time is spent on improving system stability and solving issues. The system monitoring and the problem diagnosis is of vital importance because a tiny problem may cause a great revenue loss. A failure that lasts just 1 minute may bring a loss of thousands of dollars. In the old times, our monitoring system can help engineers to monitor. It can collect service and machine operating data automatically, send the alarm automatically, and support the alarm callback function. However, it still has some problems. We manually create monitoring items, manually set their threshold to trigger alarms, and manually inspect data to find the reasons of failures. This is not suitable for our current situation. First of all, the scale of our monitoring items is very large, and the service level monitoring items exceeded hundreds of millions. It's difficult for engineers to configure the monitoring for every item. Second, the alarm threshold becomes difficult to set. It's difficult for inexperienced engineers to ensure the accuracy of thresholds. And sometimes, the threshold must follow the matrix changing. In addition, with the increase of the number of alarms, we have to balance between the annoyance and the promptness of these alarms. Third, the diagnosis method is manually inspection on curves, logs, and other information. In other words, monitoring requires a lot of human labor and human experience. Next, let's look at some examples in detail. The first example is a page view count of a service. In these two figures, the green lines denote the current data, while the blue ones show the data of the same period last week. In the left figure, in the up figure, we can see the current page view count witnessed a decrease here. Although the decrease seems not so large, the curve actually represents the page view count of the whole company, so it would cause a great loss in our revenue. In the second figure, we can see that the current count is lower than the last week count. Moreover, the gap is becoming wider and wider slowly. Our old anomaly detection method is not sensitive to this slow changing data. As a result, a great loss may already happen before our method catches it. The previous two figures shows the page view count in a time span over several hours. This figure shows the same data around 20 days. The figure tells us that the data varies continuously. Even the seasonal data has different patterns in case of holidays, and detect anomalies with historical data may give rise to high false positives and high false negatives. If we detect anomalies using threshold based on historical data, many false alarms will arise. This example is about the balance between annoyance and the promptness of alarms. In the first figure, there is only one abnormal point. And should the alarm be sent? In the second figure, there are a lot of abnormal points, and how many alarms should be sent? It's difficult for manual setting. And the last example is about inefficient problem diagnosis. Many engineers take a long time to locate the problem. According to our records, for a complicated service, the average problem locating time ranges from dozens of minutes to several hours. This is a real case. We didn't locate the problem until 10 hours later, and great loss of income and page view count has been caused. At last, we found there is a bug in our program. It didn't cause any exception until several days after it was deployed. So the troubleshooting procedure is very complex for the manual manner. There are actually much more cases out there, so some related to the alarming accuracy of the monitoring system, some related to the diagnosis, precision, and time cost. These cases urge us to build an automatic and smart system to solve the problems in monitoring and diagnosis. Then we started to build a system called Qu Bei. Qu in Chinese means cool. Bei means money. The figure shows what is Bei. Bei is the money in ancient China. We are hoping this monitoring system will improve our service and help us save money at the same time. Qu-based system is designed to three purposes. Number one, the system should collect enough data. Number two, based on historical patterns of metrics, this system should actually detect anomalies and automatically produce alarms. And number three, the system should quickly locate and troubleshoot problems. Next, I will talk about how we designed this Qu-based monitoring system. Because diagnosis needs the completeness of data, our system must collect enough data firstly. For example, the service data such as page view count, income, and the other user data. Then the machine and program data is also need to be collected, which consists of CPU usage, memory usage, disk usage, and so on. The changing events is also important, but I will not discuss the data collection in detail because it is not the focus of my talk today. And the next, anomaly detection is my key. Here is the overall architecture of our monitoring system. It consists of two parts. The offline part is a training procedure, which generates the detection configuration. The configuration goes to the online part to detect the anomaly in the production system. The decode module to trigger alarms, and the diagnosis is based on a data warehouse, including monitoring data, changing events, alarming events, and the module relationship. Next is about algorithm. Our original idea is to let a machine calculate threshold by itself without involving any manpower. The first method that comes to us for anomaly detection is 3 sigma rule. If the time series data obeys the normal distribution, the anomaly detection system learns the threshold using the average of historical data, plus or minus n times the standard deviation of historical data, and detects anomalies automatically. We found that some kinds of data obey the normal distribution and have no special pattern like seasonality, which can be addressed with 3 sigma rule. Besides the normal distribution, there are also many multi-distributions data. For example, page view count trend data have strong seasonality. As the slide shows, the data at peaks and the data at valleys differ sharply. So detecting anomalies by global 3 sigma method does not work here. As a result, we propose a segmented 3 sigma method. The essential idea of the method is to find the cycle of each time series and segment each cycle into several windows. Then we calculate the threshold based on the average and the standard deviation of the same window on historical cycles. For example, we use 15 minutes as the window size for page view counts, and each window includes 3 simple points. And we have addressed how to calculate threshold for multi-distributions. And next, how can the system categorize some special patterns? The workday versus the weekends and holidays. Because we found that the data of workday is totally different from the data of weekend, we have also studied some classification and aggregation methods and choose case test in our scenario. Case test determines the similarity of data based on whether the data has the same probability distribution. For deciding whether the data have similar probability distributions. If so, we tend to consider that the data belongs to the same category. Otherwise, it's not. When calculating the threshold, we just use the same category historical data. These thresholds are more accurate. And now we can decide which method for anomaly detection. However, this can only be used when the data is stable. In reality, data changes continuously. For example, seasonal data has different patterns if holidays fall into the data collection or analysis period. And detect anomalies with historical data may give rise to high false positives and high false negatives. For example, the figure shows the difference between workday and holiday. We can see that the data differs significantly. And if we detect anomalies using threshold based on historical data, many false alarms will arise. Then how should we solve the problem? The method we use to solve this problem is called hot winters. We modified the original hot winters method. The advantage of using this method is that it can not only capture the seasonality, but also the pattern of the trend. This way, our result shows a better fitting in seasonality and the prediction of trend. In addition, we adjusted the threshold in hot winters, and it also can solve the previous problem mentioned in our last slide. To solve the previous problems, we need historical data to train a model, such as variance and means. And however, when there is no historical data and we want to detect the change point, what should we do? We use the local regression method called LOESS. It fits the data in local area and only requires a dozen of data. If there is a huge change in the data, there will be a big difference between the fitting data and the real data. We consider it as an abnormal point. This way, we can identify this difference and solve the problems. Again, this method is used in the situation that we are lack of historical data. For example, we can detect the anomalies for a new service which we have not accumulated enough historical data. One leftover question from our previous case studies is how to detect a small decrease comparing to historical data. Because it is hard to find the small decrease based on a single point, we applied an accumulation method. We divided the original data into different time bins with the same size. And we calculate the sum. We compare the result in the same period of different days to detect the decrease or increase. The size of the time bins is about 15 minutes, 1 hour, or 24 hours. If we detect a small decrease, we will consider it as an anomaly. We may solve the 80% kinds of an anomaly by applying the above methods. But here comes a new problem. If our SRE engineers want to adjust the threshold of parameters, how to do it? Here we have two methods to solve these problems. First, SRE engineers can change the parameters threshold directly. For example, they can change 3 sigma to n sigma. Second, if SRE engineers are not familiar with meaning of parameters, they can label the anomaly points of the data. Our system can learn from the labels and change the value of parameters automatically. So far, I have covered the basic anomaly detection methods. Next, I will go over a common monitoring problem. How can we solve a huge number of alarms? Actually, frequent and sudden alarming is the result of close monitoring. For example, the cycle is 30 seconds or 1 minute. However, this will make the data unstable. So, can we compromise between real time and accuracy in monitoring? Our method is Viterbi, which is an algorithm of communication technology. It treats the alarming point as an anomaly date series. For example, after anomaly detection, the alarming series is like 010101. O means OK, 1 means anomaly. This is the input of Viterbi, and the result tells us whether this series is OK or abnormal. If it is abnormal, our system will generate an alarming message. Okay, I have introduced the monitoring methods. Another significant area is diagnosis for the anomalies. Until now, most of the diagnosis methods are manual work, and we are trying to automate this process. Actually, we have developed 3 root cause analysis methods targeting 3 cases. First is focusing on metric data analysis. Finding the root cause of which subdimensions data causes the total dimension data anomaly. Second is finding which upgrade or changing event is the root cause of the anomaly. Third is focusing on module level. One system is formed into many modules. These modules are interactive with each other. If one module communicates with another module, that means the anomalies in these 2 modules have causality relationship. First, let me introduce what is total dimension and subdimension. For example, our total page view count comes from each operator, each region, each browser, or the click of each page. Then we think the total PV count is the total dimension, and each operator's PV or each region's PV count is a subdimension. When the total page view count decreases, it's largely caused by a subdimensions anomaly. So we need to find which subdimensions decrease is the root cause. In this case, we need a data analysis method to automatically point out what is the subdimension. Our system can calculate the proportion of subdimensions in the total dimension, and then convert them to data loss during this period. Then system began to analyze what is the impact of the subdimensions on the total dimension. After sorting the order of calculated impact values, we tend to consider that the greatest effect subdimensions is the root cause of the anomaly. We also provide another way. This is a heat map about anomaly numbers. This idea is to let users more directly locate subdimensions problems. We divide an overall data into many dimensions, and users may diagnose a problem from 2 dimensions by the heat map. In this method, we can respectively divide these 2 dimensions into the horizontal and the vertical coordinate, and then show anomalies in a range of its corresponding dimension. If the dimension has lots of unusual cases in the coordinates, it is likely to be the abnormal dimension we are looking for. The figure is an example. The horizontal axis represents the platform, while the vertical axis represents the data center. The red blocks in the figure is suspected subdimension. On the other side, we find service upgrade have caused a lot of problems. Due to the complexity of systems, the upgrade may cause an impact on system stability. The figure shows we make a special treatment in dealing with the service upgrade and the time series data. For example, when a curve changes sharply, we tend to check whether it has a program upgrade recently and may take the action as the cause of the curve change. Thus, our SaaS system is required to know what kind of changes will affect what index of modules for different products. If the change and the curve has such an association, we can derive a more reliable calculation by this method. Many problems of modules are caused by other modules. If a module causes other modules, a possible fault of module may affect the other modules and the whole system. We are hoping to solve this kind of problem diagnosis. We construct a module calling graph for each product. All the abnormal events and the upgrade events were associated with the module on the graph. If an anomaly occurs, SRE engineers can find the affected module quickly, and they also can find the root cause quickly through and the related events and other information. After those functions, we hope to build an overall view of a service, including the relationship of underlying modules, the key indicators for each module, and the occurred changing events or alarming events, curves, and other informations. After setting the view, once problem occurs, even a small problem can be diagnosed quickly. For example, if a metric of a module becomes abnormal, the corresponding place in the view will directly be reddened, which will be helpful for us to quickly locate the root cause. Then our Qu-based system comes. Well, I'm almost at the end of my speech. Summarize our past. Surely, as for the automatic anomaly detection and the problem diagnosis techniques, we are still a beginner. But with our advanced research and accumulation of time and experience, we hope to detect anomalies and diagnose problems better and better. I believe the system is helpful for engineers to keep their site more reliability. Well, about the future, besides anomaly detection and problem diagnosis, there are also some other applications which can be analyzed automatically, such as characterization of workload specs, dynamic resource allocation, and identification of performance problems, and capacity management. For example, there is a system called Matrix in Baidu, just like Mesos. By using the methods of data statistics and analysis, different applications may be co-located better in data center. In a word, our opinion is that data statistics and analysis, such as statistical machine learning, is a useful tool for automating data center operations. That's all. Thank you. My English is not good, so I need a translator. Anyone have a questions? So this is our friend from Twitter. Okay.
You mentioned when you're segmenting using a segmented 3 sigma rule, an interval of 15 minutes. Was there a particular reason that you chose 15 minutes and not 20 or 30? Was it what was the trade-off that you solved in 15 minutes?
In Chinese. 对，就是我知道问题，我说我回答用什么？用陈英，用英语。OK， 有翻译吗 ？OK， in Chinese you translate it. Oh, sorry.
Go first.
其实我们这个15分钟的这个 window 是因为我们看了正常的点数应该是多少，其实我们觉得30个点是比较合适的，能让这些点更稳定，就是让这个算出来的方差更稳定。
Oh, so 15 minutes. So 15 minutes window, we calculate, we use this window because we use some data and we find out that 15 window is the best to fit our scenario, and we can cover like the 30 points here, and so that's why. So that's based on the data we have that we choose this time window.
The means and the variance is more stable for about 30 points. Thank you.
Can you say something about on your slide just towards the end, the correlation automation that you're doing? Are you investing in auto-correlation? And if so, what are you doing? How successful is that?
This question he can ask it.
I'm another senior software engineer in Baidu SI team. This work is designed by me to different application co-located in data center, just like Google Spark or methods and we have online application and offline application, just like website server, MapReduce, and LBS application. In early work in Baidu, we co-located by test and latency, based on latency of the application, and co-located with human experience. Maybe this web server and MapReduce co-located is okay, but not LBS application and web server is not okay. Maybe this is all by human experience in early work, not efficient, high efficient. Then we use the data from the data center of the performance of all application and automated the process which application can collocated with another application. Then the usage of the data center is high than before. And the application is not influenced with each other. Maybe this is the design.
Thank you.
Okay.
Okay. Any questions?
Oh, thank you. Thank you for bringing
Thank you very much.